So at this point, we have a decent grasp on what the first derivative is telling us and how to calculate it using the definition. And we've seen quite a few examples of how this can show up in real-world applications. What we want to look at today is the second derivative and a notion called concavity. So let's first review what the first derivative is telling us geometrically. So recall that if we have a function y equals f of x and it happens to be differentiable at x equals a, then the derivative gives us the slope of the tangent line at x equals a. And now we can take this notion and look at this geometrically and relate this to whether a function is increasing or decreasing. So for example, if we look here, notice that the slope of the red line here is the tangent line. In this case, it's the tangent line at x equals 2. And notice that since f is increasing here, the derivative is positive because the slope of the tangent line is positive. So the first derivative being positive is equivalent to the function being an increasing function. So that's a nice way to be able to relate increasing of a function to its derivative being positive. And we can do the same thing for a decreasing function. So again, the red line here is the tangent line at 2. And notice the slope of this is negative and the function is decreasing. So we can see the slope being negative is equivalent to the function decreasing. So we can look at a function and figure out whether it's increasing or decreasing just by looking at whether the derivative is positive or negative. So it's a super useful concept, especially in looking at applications when we want to know if some quantity is increasing or decreasing. So now the second derivative of a function is just the derivative of the derivative. So first you take the derivative of f, and then you take the derivative of that function. So we're often going to denote this as f double prime of x, or if we're using the notation of df over dx, we just put a 2 on the d and the 2 on the x to indicate that it's the second derivative. Now we might want to take more derivatives than just the second one, in which case we don't want to keep putting dashes on it for like the 10th derivative. So in that case, sometimes the second notation is better, but we'll also see another alternative notation later for higher power derivatives with the dash notation. But for now, this is what we mean by the second derivative. So the main focus of this flipped class video is going to be on what does this mean, the second derivative tell us geometrically, to kind of go along with, we saw the first derivative telling us increasing or decreasing. We want to do the same idea with the second derivative and see what that tells us geometrically. But first, let's go ahead and make sure, when we say it's the derivative of the derivative, let's make sure we actually understand what that means. So let's take a simple example of y equals x squared. Now we've calculated before, just using the limit definition of the derivative, that the derivative of x squared is just 2x. And if you don't remember that calculation, it'd be a good idea to pause the video here and go ahead and carry that calculation out and convince yourself that the derivative is 2x. So now if I want to calculate the second derivative, I want to take the derivative of the derivative. So that means I want to take the derivative of 2x. So let's go ahead and calculate that. So f double prime of x, well, that's the derivative of the derivative. So whereas we normally look at the limit as h goes to 0 with f's there, since we're taking the derivative of the derivative, we look at f prime of x plus h minus f prime of x, because f prime is the function we're taking the derivative of. Divide that by h just like normal. And now our function is f prime is 2 times x. So when I plug in x plus h, it's just 2 times x plus h minus 2x. If we distribute that 2 through, you'll have a 2x plus 2h minus 2x. Those 2x's cancel. So we just get 2h over h, which is just 2. So the second derivative of x squared is just 2. Okay, so let's figure out what's going on with the geometry here, because that's what we are actually interested in for this flipped class video. So we saw above that f prime being positive is equivalent to f being an increasing function. So that means if we, instead of if we take the same idea with the second derivative, we see f double prime as positive is equivalent to f prime being increasing, where we're just replacing the function f with f prime, so the derivative of f prime is f double prime. Okay, so same idea. Exactly, we're just shifting the function by its derivative. So we look at the derivative and the second derivative instead of the function in its first derivative. So then we might ask, well, what does it mean for the derivative to be an increasing function? So let's look at what that looks like geometrically for f prime to be increasing. So before we pop that graphic up, just remember for f prime to be increasing, that means is we increase the value of x, the slopes of the tangent line should be getting bigger. So here's a graphic of this. So notice as my x increases, the slopes of these tangent lines are increasing as well. So here, not only is the function increasing, so the first derivative is positive, the second derivative is also positive because the slopes of the tangent lines are getting bigger as I move to the right. So all the slopes are positive, but they're also getting bigger. So there's another way the slopes of the tangent lines could be increasing as x increases. So notice in this case, the function is decreasing, so my derivative at all of these points is negative. However, as I go towards the right, the derivatives are getting less negative as this tangent line is getting closer to being a horizontal line, so it's getting closer to having a slope of 0. So even though the function is decreasing, the slopes of the tangent lines are increasing as x increases. So the second derivative is also positive in this case. So if we look back at this case and the case before it, notice that the tangent lines are always below the graph y equals f of x. So we refer to a function where the second derivative is positive, which is equivalent to the tangent lines being below the graph, is a concave up. So here's a typical picture of a concave up function. So it can be increasing or decreasing like we just saw. It just means that the second derivative is positive. Now we've gone through this whole process here where we're assuming the second derivative was positive. What happens if we assume the second derivative is negative? So go through the whole thing again. So we saw right at the beginning of the video that if the derivative is less than 0, this is equivalent to the function being decreasing. So replace the f of x with f prime of x, and then we'll see f double prime of x less than 0 is equivalent to f prime of x decreasing. So same idea as before, we're just switching increasing and decreasing and positive and negative. So again, we can ask, what does it mean for f prime to be decreasing? Well, this should mean as my x value increases, the slopes of the tangent line should be decreasing. So here's a graph of this. So notice the slopes here are all positive. My function is an increasing function, so the slopes are positive. And as we move to the right, so as x gets bigger, they go from a very positive, so very steep slope, and they get closer and closer to a horizontal line where the slope would be 0. So even though this is an increasing function, so the slopes are positive, they're getting smaller as they get closer to 0. And again, we have another way to do this as well. So we can also have them start here, the function's decreasing, so the slopes are negative, but they're starting where the line's almost horizontal, so close to 0. And as we move to the right, they're getting more and more negative. So they're decreasing as we move towards the right. And again, we can notice in this case, all of my tangent lines are always above the graph. So all the tangent lines you see here are above the graph, and same thing for this one. They're always above the graph. So we refer to a function where the second derivative is negative, which is the same as saying the tangent lines are above the graph, as concave down. And here's a picture of a typical concave down function.